Thank you for the introduction. My name is Nishit Goel, and today I'll be talking about the vacuum gauges that we have fabricated based on micromachined bulk acoustic wave resonator. So I'll start up with the motivation for the work. So in microfabrication world, we use a lot of deposition and etching tools, which work in the regime of 0 to a micro-Torr regime. And we need to measure them accurately for having a process control over our processes. So there are two basic methods of measuring the pressures that we have. The first is an indirect pressure measurement system, which measures the property of a pressure which is dependent on the pressure, and hence you know the pressure of that system, and hence it is also dependent on the gas that you use for your process. So for different gases, you have to recalibrate your pressure sensors to have a better idea of the pressure that you have in the system. The other type of sensor that we have is a direct pressure measurement system, which actually which actually is dependent on a mechanical deformation of the device due to the pressure. Like we have a capacitance gauge where you have a fixed and a moving electrode, and the gap between the fixed and the moving electrode is changed by the change in pressure. However, the best we have in that regime is a capacitance manometer, and you need to have like a set of gauges to span a range of from an atmosphere to a millitorr, or let's say even a microtorr regime. So I'd like to propose a sensor based on quartz, which can do with just one device that you can use for this high range. So quartz, a little bit about the quartz. Quartz is a piezoelectric material that is widely used for timekeeping applications for its high quality factor. It's also used as a quartz thickness monitor in your deposition systems. There are various cuts available for quartz. The one that I'm using in this work is an 80 cut quartz. So, the property of that is that it has almost near zero temperature sensitivity at room temperature. So it's more stable at room temperature and has less noise due to temperature variations. And it resonates in its thickness shear mode. So the motion is perpendicular to the direction of field that you apply, and the resonance frequency of the device depends inversely, or is inversely proportional to the thickness of the device that you have. So if you can tune the thickness, you can tune the resonance frequency. The effect that we use of quartz to sense the pressure is force frequency effect. This effect is an undesirable effect for high precision frequency applications, and hence it was extensively studied in the 1960s by a lot of researchers to understand this phenomenon. So the change in the frequency is linearly proportional to the force that you apply, either transverse or in plane. And it can be explained by nonlinear elastic theory, that it just does not depend upon the second order elastic coefficient, but also on the third order elastic coefficients related to the zeroth order strains in the system. So in a nutshell, it depends upon the stress that you apply, the thickness, and the azimuthal angle, which is an angle that is related to the crystal angle of the quartz. So the sensor design and operating principles. So we have a quartz plate which is etched in certain regions using microfabrication techniques, and we clamp it around its edges, and we apply a pressure. We apply pressure on one side, and while doing so, we are measuring its impedance characteristics. And the pressure is measured in two ways: in the low pressure regime or in high vacuum regime. We set a resonance frequency constant, and we are measuring the susceptance change. And as you can see, we have a very high slope there, so that will give us an advantage in terms of sensitivity. However, this method is only applicable till you reach the inflection point in terms of frequency, and hence once you overcome that, we track the resonance frequency peak to measure the pressure. The fabrication is fairly simple for the device. We start with a 100 micron thick 1-inch quartz wafer. We put chrome gold on the top, which acts as a seed layer for the electroplating. We do our first lithography, define our etch regions, and put nickel as a hard mask. Then we do dry etching for a long time to get to the right thickness that we would want. And by controlling the etching time, you can control the thickness and hence the resonance frequency. And then in the end, we strip. So we strip all the metals after this step, and then we put the electrodes on the top and the bottom side of the resonator. Once the device is fabricated, we put it in a dual inline package, and we clamp the edges by using an RTV silicone epoxy on the edges so that it has lower stresses. And that custom package has a hole at the back so that we can apply differential pressure to it. And then it is put in a custom package that provides a hermetic sealing on the ceramic package that we have made, and then we can do a testing on it. So that custom package is the DUT as shown in this schematic, and what we can do here is then we can first we pull the vacuum on both sides of the diaphragm, and then once we reach the high pressure or high vacuum regime, we isolate the two sides by using the isolation valve, and we introduce the nitrogen gas and stress one side of the quartz plate, and we measure the pressure by using a capacitance gauge, and while we are also measuring the impedance characteristics using an agent impedance analyzer. So we did measurements with the 3 different thicknesses of quartz, the 36 megahertz, the 36 microns, 20 microns, and 8 micron thick device. And as we can see that as you reduce thickness, the sensitivity of the device increases, which is evident from the fact that your stress is increasing in the resonator region. However, it does match the trend as proposed by the theory, but it doesn't match fully, because what we have in our system is we have a pliable epoxy, so we are losing some stresses there, and also when we go thinner, we might have some higher order effects which we might not be considering while we are making our model predictions. To understand the resolution of the device, and as is done in the frequency measurement systems, we measure the Allen deviations of the device. So it is shown for the 3 thickness resonators that I've made. And the best resolution which we were able to achieve was for a 20 micron thick device. Now these noise sources, the noise in these resonators depends on a lot of factors. And the biggest source that we were able to isolate was the vibrations due to the vacuum generation setup. So we need to work in that area, and hence we can improve the resolution for these devices. Now we talk about the performance of these devices in the high pressure regime, that is from a 0 to let's say an atmosphere. I measured it for a 48 megahertz resonator. It was pretty linear, and we were able to go up to 410 torrs. What we were seeing is that after around 450 torrs, the devices were breaking because it was reaching its yield point, and hence we need to make a better mechanical design for the resonators that we are making. Another interesting property that we found for these devices was that when you apply pressure, so the response of the devices was dependent upon which side you're applying the pressure at. So if you're applying pressure on the top, on the edge side, the resonance frequency would shift down. And if you're applying pressure from the bottom side, the resonance frequency would shift up. And it was understood by doing a COMSOL simulation of the stress states in the resonator region. It was found that in the case when you're applying pressure from the top side, there's a dominant tensile stress that is there in the resonator region, and hence the frequency is shifting down. And similarly, for the case of applying pressure from the bottom side, there was an increase in the resonance frequency because of the compressive stresses that were dominant in there. So to conclude, we were able to show a wide range pressure sensor based on the quartz diaphragms, And we carried out a study with changing thickness and to see how the sensitivity is how the sensitivity is behaving with that. And we were able to achieve a sensitivity of 0.74 hertz per millitorr for 8 micron device, and demonstrated a millitorr of resolution for 20 micron device. And we saw that the sensor is pretty linear in both the low pressure and the high pressure regime. The future work would be to have a better mechanical design to achieve first sub-millitorr resolution, which was the aim or the motivation for this work. And the other would be to have better vibration isolation so that we have better resolutions. And the third would be to have low stress epoxy study, because right now what we are doing is we are pulling the vacuum continuously and we have that silicon epoxy. So we would want to get rid of that and use some getters so that we have a constant low pressure at one side. So a very good vacuum isolation and low stress epoxy would be needed for that. Thank you.